The Works of Archimedes, on the Sphere and Cylinder, Book 1, Propositions 1 to 20. This video is the first video in a series of videos covering some of the parts in Thomas Heath's translation of the Works of Archimedes. These videos will often go into some detail and are not intended to be a brief introduction to Archimedes or a short history of Archimedes and so on. These videos will assume a certain level of knowledge and ability in mathematics and geometry. I'll often be reeling off a lot of information in a short space of time, so you may need to pause the video on occasion. It may also help if you take notes from time to time. The videos will probably best serve those who are going through the Works of Archimedes, and so it may help if you have a copy of Heath's The Works of Archimedes to hand while watching these videos. The Works of Archimedes is in the public domain and is available to download legally for free from the internet. Thomas Heath's version of the Works of Archimedes, as you'll immediately notice, uses fairly modern notation, which of course makes things easier for modern readers. However, since such notation was obviously not available to Archimedes, then Archimedes himself would have used very different modes of presentation. However, I'll often just stick with Heath's style of notation in these videos. The Works of Archimedes are not necessarily entirely self-contained works. Some of Archimedes' works are no longer extant, and he may have used results from these no longer extant works in the works that we find in this book. Therefore, there may be some steps taken in these works that don't seem to be fully justified. It may be possible to reconstruct some suitable justifications in some cases, and in other cases it may not be possible. Some of the unexplained steps that Archimedes takes in his proofs or demonstrations can sometimes be explained by relying on results from Euclid. Archimedes, it seems, would have been aware of the results of Euclid, and would have used these results in his own works. Indeed, we see on page 16, that's 16 in Roman numerals, of the introduction, it appears that he, Archimedes, spent a considerable time in Alexandria, where it may be inferred that he studied with the successors of Euclid. However, in the book The Archimedes Codex, revealing the blueprint of modern science by Netz and Noel, on page 39 we see, but Archimedes wouldn't think very highly of them, the works of Euclid, as they consist mainly of basic mathematics. Archimedes was an advanced mathematician, writing for people who knew much more than just the contents of Euclid's elements. Of course, this doesn't mean that Archimedes disregarded Euclid's works or was contemptuous of them, but possibly saw the results contained in the elements as too basic to be of any real interest, in the same way that an expert in some field of work nowadays will probably not be particularly interested in the rudimentary aspects of their field of work, and though the expert may depend on those rudimentary aspects, they're not in and of themselves of interest to the expert. We're told in the introduction that Archimedes was probably born around 287 BC and died around 212 BC. This means that it seems reasonable to apply the results of Euclid to justify some of the aspects of Archimedes' work. However, it may not be reasonable to apply the results of, say, Apollonius, since Apollonius is believed to have lived from around 240 BC to around 190 BC. Therefore, obviously, Archimedes wouldn't have known of Apollonius' results, and if these dates are correct, then Apollonius would have only been a young man when Archimedes perished. I will in some cases try to provide some explanations for some of the unexplained steps using results from Euclid. However, if this is done every time, then it will get very tedious and pedantic. I'll give an example or two to show how things might go, particularly in the first video or so of this series, and even then I'll have to draw the line somewhere, so to speak. But going forward, generally, I'll just try to indicate which of Euclid's propositions and so on may be useful to refer to without actually going through the full justification. Just as in modern geometry and mathematics, not every result that's required in a proof or demonstration is explicitly mentioned. There does come a point where something has to give, and it's just accepted that certain results are being used implicitly. So in some cases we do have to consider the possibility that some results that are used implicitly in Archimedes' arguments. And maybe some results were so familiar to the ancient Greek geometers that they just didn't even bother mentioning them, whereas the same results may not be so familiar to us nowadays, though this doesn't mean that those results are unknown to us. The introduction is quite lengthy. In fact, it can be quite overwhelming in places, and I certainly won't be going through the introduction in too much detail. The introduction could probably be skipped altogether and you could just get straight to the first section of Archimedes' work on the sphere and cylinder. However, the introduction does give some useful information regarding how Archimedes' work is related to the works of others. There are some lengthy passages relating to biographical details concerning Archimedes and how Archimedes' writings have been passed down through history. If you're interested in these kinds of details, then some of this information is there, and you'll also be directed towards other works which will go into further detail should you want it. I've tried to pick out some of the key passages from the introduction, and rather than just give them all in one go, I'll tend to give the relevant quotes from the introduction at the appropriate points in the videos. It may be worth skim reading the introduction initially because there are some bits of information that are useful to refer to when reading through the main works. However, many parts of the introduction which are relevant at certain points in the main work are often referenced in footnotes anyway, but there may be other smaller passages which you'll find to be useful at certain points, in which case it may be well to make a note of these passages and try to refer them to the appropriate part of the book. And of course, it may be necessary to read and reread certain parts of the introduction. There's a lot of information there, and the significance of a certain passage may not become clear until much later. Just a couple of final remarks before we start. It may often be useful to understand that an expression such as AB times AC, as representing the area of a rectangle with sides of lengths AB and AC respectively, and therefore AB times AC is simply the length multiplied by the width. It's common in Euclid, at least in Heath's translation, to read something more along the lines of the rectangle contained by the lines AB and AC. Indeed, in Euclid, the area of a rectangle is never actually said to be the width multiplied by height, and nor is the area of a triangle in Euclid ever said to be half base multiplied by perpendicular height. But these formulae will be used and taken as given in Heath's translation of Archimedes. I've added further detail to what's already there at various points throughout in order to give a more detailed justification for some of the steps in the arguments. But these details are only supposed to be illustrative. I'll be showing some, but by no means all, of these additional explanatory steps on the screen during this video. More detailed explanations will be given verbally, and yet further detailed explanations you'll have to derive for yourself. Therefore, the arguments that I've added may not be completely satisfactory in and of themselves, and I'm sure that there will be plenty of people who will be able to pick holes in my arguments. The justifications are often intended to merely indicate what I consider to be the main points worthwhile considering. I don't make any claims that these details are exactly what Archimedes or any other Greek geometer would have done. I'm not an ancient Greek scholar, so I don't know exactly how they would have thought about these things. I've tried to avoid using modern concepts and techniques in the justifications, and this means that there are occasions where I've had to avoid certain formally valid arguments, but which would potentially not be valid under certain interpretations. But there is a limit to this approach. If I were to completely abandon modern notions of algebraic manipulation, then it quickly becomes very wearying to carry out even the simplest arguments. I've also tried to use a variety of different techniques and approaches. As with many things in geometry and mathematics, there's usually more than one way that a problem can be solved. And finally, during these videos, rather than saying the ratio of A to B is equal to the ratio of C to D, I'll often just say A to B is equal to C to D, or something similar. Otherwise things will get unbearably repetitive. So let's make a start. Definitions. Definition 1. Bent lines here, as the footnote on page 2 indicates, applies to curved lines of continuous curvature, but also lines made up of any number of lines which may be either straight or curved. Bent line is, of course, to be distinguished from straight line. And it may be the case that some part of a bent line other than the extremities or the endpoints lies on the straight line joining its endpoints. And this may happen if the bent line has any straight parts, made up of straight lines for example. However, provided that the bent line doesn't at any point pass on to the other side of the lines which join its endpoints, then it's one of the bent lines that definition 1 is asserting the existence of. A reworded definition of definition 1 may go as follows. There are in a plane certain terminated bent lines, each of which lies either wholly on the same side of the straight line joining its extremities, or has no part on the other side of the straight line joining its extremities. Definition 2. In this definition, it may be that there is a pair of points A and B on the bent line such that the line joining A and B lies entirely on the lines joining the extremities, but provided that none of the lines joining a pair of points on the bent line cross over the line joining the extremities and doesn't cross over to the other side of the bent line, then the bent line is concave in the same direction. Definitions 3 and 4 are analogous to definitions 1 and 2. For definition 5, we can visualize the solid sector that definition 5 is talking about as the volume of revolution generated when the shape shown on the screen now is rotated about the dashed line. And definition 6, in a similar way to the definition of solid sector, a solid rhombus can be visualized as the volume of revolution generated when the shape shown on the screen now is rotated about the dashed line. The volume of revolution generated will effectively be two cones with equal bases joined together. Note that the cones do not have to be of equal height. The term solid rhombus is also explained more on page 166 of the introduction. Moving on to the assumptions, and I won't go through all of the assumptions, most of them are self-explanatory. However, assumption 5 says that if the magnitude which is that by which the greater exceeds the lesser is added to itself sufficiently many times, then it will exceed any given finite magnitude. This assumption therefore excludes the possibility of infinitely small or infinitely large magnitudes appearing. For proposition 1, note that the arc PQ of the circle is concave in the same direction as the bent line PAQ, which is made up of the two line segments PA and AQ. If we were to draw a straight line joining the points P and Q, then it's clear that the arc PQ lies between the bent line PAQ and the straight line PQ, with just the endpoints of the arc on the line PQ and on the bent line PAQ. But at no point does the arc cross from one side of the line to the other, or from one side of the bent line to the other. So the arc PQ satisfies the conditions of assumption 2 on page 4. Therefore, the arc PQ is the lesser of the two. Hence the inequality, PA plus AQ is greater than the arc PQ, and the result easily follows. Proposition 2. The magnitudes that proposition 2 is referring to may represent lengths, areas, or volumes, etc. A magnitude of a certain type can be compared with another magnitude of the same type to determine whether they're equal or unequal, and we can speak of the ratio of two magnitudes of the same type, though we cannot speak of the ratio of magnitudes of different types. Thus, lengths can be compared with lengths, areas with areas, volumes with volumes, and so on, but we can't compare, for example, a length with a volume. Magnitudes, though not forced to be lengths, will often be represented or visualized by lines of certain lengths, in a similar way that in modern mathematics and geometry, lengths, areas and volumes, etc. may all be represented by numbers. One magnitude in the proof of proposition 2, AB, is represented by two letters, denoting its endpoints, and the other D is represented by a single letter. This seems to be simply because the magnitude AB will be divided up in some way and it will be convenient for the endpoints to have names, whereas the magnitude represented by D will not be divided up, and so we don't really need to have specific names for the endpoints. Many of the arguments used in the proof of proposition 2 have a very Euclid Book 5 feel to them, and I'd recommend anyone who's not familiar with Euclid's elements download a copy, again freely and legally available for download, and have it to hand for reference. Assumption 5 is used to form AF, which is CA added to itself sufficiently many times to exceed the magnitude of D. Since AF and HG are equal to the same multiple of AC and EH respectively, then we have by a variation of Euclid 515, AC to AF is equal to EH to HG as required. That AC to AF is less than AC to CB is due to Euclid 5.8. We know then that the ratio of EH to HG is less than AC to CB, so by a variation of componendo, see Euclid Book 5 propositions 17 and 18, we have EH plus HG to HG is less than AC plus CB to CB. But EH plus HG is just EG, and AC plus CB is AB. Thus we have EG to HG is less than AB to CB, but of course CB is equal to D, therefore EG to HG is less than AB to D as required. Proposition 3. The diagram which is given for this proposition is a bit misleading since it shows A, F and B all represented by lines. However, A and B, as we're told, are magnitudes and only F is a line with a certain length. In the proof of proposition 3, the construction of LM perpendicular to LK such that Km equals F can be done using Euclid 1.11 and Euclid 1.3. The angle DOC can be bisected using Euclid 1.9, and similarly for the repeated bisections. Also note that on pages 47 and 48, that's 47 and 48 in Roman numerals of the introduction, is quoted a lemma which is Euclid 10.1. Given two unequal magnitudes, if from the greater a part be subtracted greater than half, and if from the remainder a part greater than half be subtracted, and so on continually, there will be left some magnitude which will be less than the lesser given magnitude. Therefore, by continually bisecting the angle DOC, we will eventually arrive at an angle which is less than twice the angle LKM. Suppose that angle DOC is bisected n times, then the side NC will be one side of a regular polygon inscribed in the circle with a total of 2 to the power of n plus 2 sides. Again, NOC can be bisected by using Euclid 1.9. The tangent at P can be constructed by drawing the perpendicular to OP at P, which uses Euclid 1.11, which in turn, by Euclid 3.16 porism, will be a tangent to the circle at P. The inequality MK to LK is greater than OC to OH seems innocuous enough, but the justification of this inequality is conspicuously absent. Of course, we can take Archimedes' word on this, after all, he was quite a smart guy, but let's just have a look at how this inequality could be justified. The argument that I give is only meant to give an idea of what might be involved if you really wanted to go into this level of detail. Even in the following argument, there may be some things that, in turn, may need some further justification, but let's have a look. We start with the triangles KLM and OHC, where we know that angle HOC is less than angle LKM. Suppose that KL is less than OH, and in this example I won't cover the cases KL equals OH or KL is greater than OH, but I'll leave these for you to do yourself if you want to. Then by postulate 2 of Euclid and Euclid 1.3, KL can be produced to L primed, where KL primed is equal to OH. Using Euclid 1.11 and postulate 2, draw the perpendicular to KL primed at L primed, meeting KM produced at M primed. And use Euclid 1.23 and postulate 2 to construct the angle L primed KQ equal to angle HOC at K, so that KQ meets L primed M primed at Q. Then since angle KL primed Q is equal to angle OHC, and angle L primed KQ is equal to angle HOC, and KL primed is equal to OH, then by Euclid 1.26, KQ is equal to OC, and L primed Q is equal to HC. Now consider the line L primed Q M primed. Use Euclid 1.46 to construct the square on L primed M primed and L primed Q respectively. Therefore, by common notion 5, since the square on L primed Q is part of the square on L primed M primed, then the square on L primed M primed is greater than the square on L primed Q. So by Euclid 5.8, the square on L primed M primed to the square on KL primed is greater than the square on L primed Q to the square on KL primed. And further, by componendo, we have the square on L primed M primed plus the square on KL primed to the square on KL primed is greater than the square on L primed Q plus the square on KL primed to the square on KL primed. But by Euclid 1.47, which is Pythagoras' theorem, we have that the square on L primed M primed plus the square on KL primed is just equal to the square on KM primed, and the square on L primed Q plus the square on KL primed is equal to the square on KQ. Therefore, the square on Km primed to the square on KL primed is greater than the square on KQ to the square on KL primed. So by Euclid 5.10, the square on Km primed is greater than the square on KQ. Now construct a rectangle on KQ with height the same as the square on Km primed. Then by Euclid common notion 5, the rectangle on KQ is greater than the square on KQ. So by Euclid 5.8 we obtain the square on Km primed to the square on KQ is greater than the square on Kn primes to the rectangle on KQ. But by Euclid 6.6, the square on Kn primed to the rectangle on KQ is equal to Kn primed to KQ, since the square and the rectangle have the same height. Therefore, by Euclid 5.13, the square on Kn primed to the square on KQ is greater than Kn primed to KQ. And since the square on Kn primed is greater than the square on KQ, then Kn primed is greater than KQ. This conclusion could of course be arrived at in probably a line or two using modern algebraic techniques. So by Euclid 5.8 we have Kn primed to Kl primed is greater than Kq to Kl primed. But by Euclid 6.4, since triangles Kl primed, M primed and KLM are equiangular, using Euclid 128, then Kn primed to Kl primed is equal to Km to Kl. So by Euclid 5.13 we have that Km to Kl is greater than Kq to Kl primed, and therefore we have by Euclid 6.4, since triangles Kl primed Q and OHC are equiangular, OC to OH is equal to KQ to Kl primed. Therefore by Euclid 5.13 we have Km to Kl is greater than OC to OH as required. Many of the ratios involving inequalities found in Archimedes can probably be justified in analogous ways, and it's a good exercise to try to do this for a couple of them, because it can help to try to get into a certain way of seeing things, rather than looking at everything with a modern perspective. Of course, this level of analysis is very time consuming and would be exhausting, so clearly I'll only be providing justifications on this level of detail if I think that there's a real reason to do so. Even some of the steps in the above justification require further justification themselves, and I openly admit to the clear shortcomings of the argument just given, but to attempt to justify everything in the smallest detail would quickly descend into farce. Going forward, though I'll often give some detailed justifications, I may use some more algebraic notation from time to time to keep things short. So just to finish off this proposition, since OC is equal to OP, then by Euclid 5.7 we have that OC to OH is equal to OP to OH. And so by Euclid 5.13 we have that MK to LK is greater than OP to OH. And the rest of the inequalities follow easily, but I'll leave that up to you to have a go at yourself if you want to do so. Some of the propositions which are proved in this first part of On the Sphere and Cylinder Part 1 will seem to be quite a random mix. However, as far as I can see, all of the propositions are used in later proofs, and they do all gradually build up to a climax. Proposition 4. This proposition is similar to the previous proposition, the difference being that in Proposition 3 the whole circle was involved, whereas in Proposition 4 we're only interested in a sector of a circle. Again, Proposition 5 seems to be very similar to Proposition 3. The difference being is that Proposition 3 was concerned with the ratio of the side lengths of the polygons constructed. Proposition 5 is concerned with the areas. When we see the circumscribed polygon has to the inscribed polygon a ratio less than the greater magnitude has to the less, this is referring to the areas of the polygons, even though area is not explicitly mentioned. The mean proportional in this proposition F can be constructed using Euclid 6.13. And the definition of duplicate ratio, which can be found in Euclid Book 5, is given as follows in Heath's version of Euclid's Elements. When three magnitudes are proportional, the first is said to have to the third the duplicate ratio of that which it has to the second. So this definition can be explained as follows. If the three magnitudes are A, B and C, with A to B equal to B to C, then we have A to C is equal to A squared to B squared. And clearly this is using modern algebraic notation. B may be described as a mean proportional between A and C. More simply, if A and B are magnitudes, then the duplicate ratio of A to B is A squared to B squared. It may be that, although the definitions may seem to us quite clumsy, it's possible that the definitions in Euclid, etc., are given in such a way which harmonized with the way that the concepts were used by the ancient Greeks. Continuing with Proposition 5, at a point O, construct a line OX of the same length as the side of the circumscribed polygon using Euclid 1.2, and cut off from OX the line OY of length equal to the side of the inscribed polygon using Euclid 1.3. The side length of the circumscribed polygon must of course be greater than the side length of the inscribed polygon. In a similar way, at another point O', construct a line O'D and cut off a length O'F so that O'D to O'F is equal to D to F. On the line O'D, cut off a length O'E so that OX to OY is equal to O'E to O'F using Euclid 6.10. Then by Euclid 5.13 we have that O'E to O'F is less than O'D to O'F. And so by Euclid 5.9 it follows that O'E is less than O'D. Construct the rectangle on OY which has the same height as the square on OX, and similarly a rectangle on O'E with the same height as the square on O'F. Then by Euclid 6.1 we have that the square on OX to the rectangle on OY and OX is equal to the rectangle on O'E and O'F to the square on O'F. Similarly, the rectangle on OX and OY to the square on OY is equal to the square on O'E to the rectangle on O'F and O'E. Then by Euclid 5.23 we have the square on OX to the square on OY is equal to the square on O'E to the square on O'F. Now O'E is less than O'D, and so the square on O'E is less than the square on O'D by common notion 5. So by Euclid 5.8, the square on O'E to the square on O'F is less than the square on O'D to the square on O'F. Thence by Euclid 5.13 we have the square on OX to the square on OY is less than the square on O'D to the square on O'F. But since the circumscribed polygon and the inscribed polygon are similar, they are to one another as the square on their sides by Euclid 6.20. So the circumscribed polygon to the inscribed polygon is equal to the square on OX to the square on OY. Hence the circumscribed polygon to the inscribed polygon is less than the square on O'D to the square on O'F. So the circumscribed polygon to the inscribed polygon is less than d squared to f squared as required. Moreover, since f is a mean proportional between d and e, then d squared to f squared is equal to d to e. But since d and e were constructed with d to e less than b to c, then the circumscribed polygon to the inscribed polygon is less than b to c. The demonstration of proposition 6 is not explicitly given, we're just told, similarly we can show that, and so on. Just before proposition 7, Archimedes occupies himself with the problem of circumscribing a polygon about a circle or sector, such that the area between the circumference of the circle, or perimeter of the sector, and the circumscribed polygon is made smaller than some given area. The corresponding problem for polygons inscribed in a circle or sector, that is, where the area between the inscribed polygon and the circumference or perimeter is made smaller than a given area, is covered in the demonstration of proposition 2 of book 12 in Euclid's Elements, the details of which I won't cover here. But the first part of the proof, that is, of the problem that Archimedes is concerned with, is straightforward. The inequality c to a is less than a plus b to a can be explained as follows. Since the inscribed polygon I is part of the circle A, then by Euclid common notion 5, the whole is greater than the part, we have that A is greater than I. So by Euclid 5.8, we have that c to a is less than c to I, and hence by 1 on page 9, we have c to a is less than a plus b to a. Then by Euclid 5.10, we have that c is less than a plus b, or by using a variation of separando on c to a is less than a plus b to a, we get c minus a is less than b. And the expression c minus a represents the area of the circumscribed polygon minus the area of the circle A, and so this area has been made smaller than the given area B as required. In proposition 7, an isosceles cone is Archimedes' term for a right circular cone. That is, the surface of revolution formed by rotating a right-angled cone about either side containing the right angle. I'll give a simple algebraic justification for this proposition. The surface of the pyramid minus the base is equal to n times the area of triangle AOB, since the triangles are all congruent. And this is equal to n times a half times AB times the perpendicular height of AOB, which is equal to a half times n times AB times the perpendicular height of AOB, which in turn is equal to a half times the perimeter of the inscribed polygon times the perpendicular height of AOB, since the inscribed shape is regular. Proposition 8 can be easily proved using a similar method to the previous proposition, so I won't give any further details here. Proposition 9 would seem to follow immediately from assumption 3 on page 4, but this is not the case. The triangle AOB has the same extremities as either part of the curved surface of the cone cut off by the triangle AOB, plus its corresponding part of the base. Therefore, by assumption 3, it's either of these two surfaces that we can say is greater than triangle AOB, but we cannot deduce from assumption 3 alone that either curved surface on its own must be greater than the triangle. The arc ACB can be bisected using Euclid 3.30. The inequality the triangle OAC plus the triangle OBC is greater than the triangle OAB is not, in my opinion, at all trivial. This may be a case of Archimedes using a well-known result and taking it for granted, or maybe I've just missed something really obvious about this. Nevertheless, something irked me about this inequality, and I couldn't seem to just accept it, so after having a think about it, I believe that I've got a justification for it, but in a very rough form, which would take a lot of time to make properly precise. So I'll omit the full details of my justification here on the grounds that it would simply take too long to explain. That's not to suggest that it uses complicated techniques, because actually my solution uses very humble techniques. But I'll give a very quick rundown of the way that I see things. Note that we're dealing with a very particular type of pyramid here, where all of the legs of the pyramid are equal in length. Maybe this could be referred to as an isosceles pyramid. Also, our pyramid, by its very construction, must have two congruent faces. These are the faces AOC and BOC. For a more general pyramid, then the above inequality may not hold. So given the information that we have about this pyramid, there are, as far as I've been able to determine, 5 separate cases to consider. The first case is that angle AOB is greater than angle AOC, and in this case it may be useful to use Euclid 1120 to deduce that angle AOC plus angle BOC is greater than angle AOB. The second case is that angle AOC is greater than angle AOB, with angle AOC acute or right angle. In this case, I also needed to use Euclid 121. The third case is that angle AOC is greater than angle AOB, with angle AOC obtuse and angle AOC plus angle AOB less than or equal to 2 right angles. The fourth case is that angle AOC is greater than angle AOB, with angle AOC obtuse and angle AOC plus angle AOB greater than 2 right angles. And the fifth and final case is that angle AOB is equal to angle AOC, and this case is fairly trivial. Of course, in each case we have that angle AOC is equal to angle BOC. And I realise that this inequality may follow easily from some result using modern geometrical techniques and so forth. However, I'd like to try to avoid using modern techniques if I can because 1. The ancient Greeks didn't have access to them, and particularly Archimedes, and 2. I'm often ignorant of such techniques anyway. At the bottom of page 11 we see a genuine application of assumption 3 and 4. And it's worth noting that the arguments in this demonstration do not depend on whether the major arc AB or the minor arc AB is considered. As can be seen in this demonstration, it doesn't quite have the same level of generality that a modern demonstration or proof would demand. That is, it's indicated in the demonstration that the arcs AC and CB are continually bisected to ultimately leave segments which are less than D. However, in the demonstration, only 4 segments are considered, which from a modern perspective wouldn't necessarily reflect the full generality of the situation. This can be seen fairly often in Greek geometry, where a demonstration is given which, from a modern perspective, doesn't capture the full generality of the proposition to be proved, though it can easily be seen that the result will hold more generally. For example, and to make another reference to Euclid, in Euclid 145 we see the problem to construct in a given rectilineal angle a parallelogram equal to a given rectilineal figure. This is to apply to any rectilineal figure, but Euclid merely uses a quadrilateral, when any rectilineal figure could in fact be a polygon of any number of sides whatsoever. Of course though, the sorts of techniques that we have now to deal with this level of generality were often not available to the Greeks. Returning to the demonstration of proposition 9, the reference to proposition 6 is the second statement on page 9, which refers to an argument, proposition 2 of book 12 of Euclid's Elements. And the remainder of this demonstration doesn't really present any difficulties. The diagram in the book for proposition 10 shows a kind of top-down view of the cone. The arc AB can be bisected using Euclid 330, which will require the construction of the perpendicular bisector of chord AB, which will, by 3.1 porism, pass through the centre. Thus a line drawn at right angles to the perpendicular bisector of AB at C will be, by Euclid 3.16 porism, a tangent to the circle at C. Moreover, since this tangent, a line which touches the circle at C, is perpendicular to the perpendicular bisector of chord AB, then it must be parallel to the chord AB by Euclid 127. ED plus DF is greater than EF by Euclid 120. And note that the generators of the cone are equal since the cone is an isosceles cone. So now starting with AD plus DB is greater than AE plus EF plus FB, then we have AD plus DB times OA is greater than AE plus EF plus FB times OA. And this can possibly be justified by constructing rectangles on a common base of heights AD plus DB and AE plus EF plus FB respectively. Then since AD plus DB is greater than AE plus EF plus FB, the rectangle with height equal to AE plus EF plus FB will be part of the rectangle with height equal to AD plus DB. Therefore, by common notion 5, the inequality follows. By Euclid 2.1, we have that AD times OA plus DB times OA is greater than AE times OA plus EF times OA plus FB times OA. But OA is equal to OB is equal to OC, as already remarked, since the cone is isosceles, its generators are all equal in length. So possibly considering Euclid 136, we have AD times OA plus DB times OB is greater than AE times OA plus EF times OC plus FB times OB. And skipping a few of the details, we arrive at the result the triangle OAD plus the triangle ODB is greater than the triangle OAE plus the triangle OEF plus the triangle OFB. Now the area G is such that triangle OAD plus ODB is equal to triangles OAE plus OEF plus OFB plus G. The first case covers the case where G is greater than or equal to L, and there's nothing particularly difficult with the argument used. The diagram on page 13 helps to visualise what's happening. But at the end of the proof of this case we have that triangle OAE plus OEF plus OFB plus L is greater than the surface OAH-CKB. But we also have that since G is greater than or equal to L, that triangles OAE plus OEF plus OFB plus G is greater than or equal to triangle OAE plus OEF plus OFB plus L. So triangles OAE plus OEF plus OFB plus G is greater than the surface OAH-CKB. And also since triangles OAD plus ODB is equal to OAE plus OEF plus OFB plus G, then triangle OAD plus triangle ODB is greater than the surface OAH-CKB. And in the second case we assume that G is less than L, and the construction of the polygon in the paragraph at the bottom of page 14 is due to proposition 6, the third statement. Given a circle or sector and an area, it's possible to describe a polygon about the circle or sector such that the area remaining between the circumference and the circumscribed figure is less than the given area. The rest of this argument follows a very similar line of argument of the first case. Note that in this case, M is less than G. Proposition 11 is concerned with the surfaces as shown in the diagram. In the diagram, the minor part of the cylinder that is cut off by the plane is shown, but the proposition applies equally to the major part of the cylinder cut off. And similarly, proposition 12 is concerned with the surfaces as shown in the diagram. Propositions 11 and 12 may seem obvious at first glance, and may appear to follow immediately from the assumptions on page 4. But again, we have to be careful here since the two surfaces in question do not have the same extremities, and so assumptions 3 and 4 would not be applicable to them. In proposition 13, h is a mean proportional between CD and EF, which means that we have CD to h is equal to h to EF. The construction of h can be carried out by means of Euclid's 613. And the first case is to assume that b is less than s. The polygon circumscribing b and the polygon inscribed in b, such that the ratio of the former to the latter is less than the ratio s to b used as proposition 5. Note that the polygons constructed using proposition 5 will be regular polygons. It may be the case that polygons may be described using some other process which are not regular polygons and which still satisfy the inequality, but this seems like an unnecessary complication. We may assume that the polygons are regular, and so I'll make this assumption going forward. The polygon circumscribing A, which is similar to the one circumscribing B, just constructed, can be obtained by carrying out the exact same sequence of steps as was carried out to make the construction of the polygon circumscribing B. The prism constructed on this polygon about A is formed by setting up straight lines at right angles to the plane of the polygon at each vertex, using, say, Euclid's 11.12. And each perpendicular having length the same as the height of the cylinder using Euclid 1.3, and then the free ends of these perpendiculars being joined using postulate 1. More applications of Euclid go on in the construction of KD and FL, which I won't go into here. The triangle KDM is equal to the polygon about A, and the parallelogram EL equals the surface of the prism excluding bases, is an application of proposition 8. That the polygons A and B are in the duplicate ratio of their side lengths is a consequence of Euclid's 620. Roughly speaking, these polygons can be split into an equal number of similar right-angled triangles, with perpendicular heights equal to radius A and radius B respectively. Therefore, the sides of the polygons are in the ratio the radius of A to the radius of B. And so the ratio of the squares on the sides of the polygons is equal to the ratio of the squares on the radii of the respective circles. So triangle KDM to polygon about B is equal to MD squared to H squared. Since triangle KDM is equal to the polygon about A, MD is equal to the radius of A, and H is equal to the radius of B. But MD squared to H squared is equal to MD squared to CD times EF, since H is a mean proportional between MD and EF. Then we have H squared is equal to CD to EF. Now CD is equal to twice MD. Then CD times EF is equal to twice MD times EF. And so CD times EF is equal to MD times twice EF. And finally CD times EF is equal to MD times NF. Therefore MD squared to CD times EF is equal to MD squared to MD times NF. And by Euclid 6.1, triangles and parallelograms under the same height are to one another as their bases. We obtain MD squared to MD times NF is equal to MD to NF as required. Again, using Euclid 6.1 and noting that DK is equal to FL, we obtain MD to NF is equal to the triangle KDM to the triangle LFN as required. So we have triangle KDM to the polygon about B is equal to the triangle KDM to the triangle LFN. And so by Euclid 5.9, we have that the polygon about B is equal to the triangle LFN. And using Euclid 141, it follows that triangle LFN is equal to the parallelogram EL, which, as we've already seen, parallelogram EL is equal to the surface of the prism about A. On page 18, where the word alternately is used, this is an application of a variation of Euclid 5.16. And the rest of case 1 follows easily. Note that the comments following proposition 11 and 12 are used to deduce that the surface of the prism about A is greater than S, where S was used to denote the surface of the cylinder. Moving on to the second case, there's a couple of differences to take account of. Again, we use proposition 5 to construct polygons satisfying the inequality shown. Note that in this case we have the ratio B to S, whereas in the first case we have the ratio S to B. In the first case we had triangle KDM is equal to the polygon about A. Since the length KD was equal to the perimeter of the polygon about A, and splitting the polygon about A into triangles, each triangle had perpendicular height equal to the radius of A, in other words equal to dm. However, in this case we have triangle KDM is greater than the polygon inscribed in A, rather than equality. This is because, although the length KD is again equal to the perimeter of the polygon, and dm is equal to the radius of A, if we split the inscribed polygon into triangles as before, the perpendicular height of each triangle, though all equal to each other, is less than the radius of A, that is less than dm. The derivation of the equality, polygon in A to polygon in B, is equal to triangle KDM to triangle LFN, is derived in a very similar way to in the first case. However, since triangle KDM is greater than the polygon in A, then by Euclid 5.8 we have that the triangle KDM to the triangle LFN is greater than the polygon in A to the triangle LFN. So by Euclid 5.13 we obtain the polygon in A to the polygon in B is greater than the polygon in A to triangle LFN. And finally, by a variation of Euclid 5.10, we obtain that the triangle LFN, or the surface of the prism, is greater than the polygon in B. Since the polygon about B must be greater than B, then by Euclid 5.8 we have B to S is less than the polygon about B to S, giving by Euclid 5.13, or at least a variation of this proposition, the polygon about B to the polygon in B is less than the polygon about B to S, and therefore again by a variation of Euclid 5.10, the polygon in B is greater than S. But by the comments following proposition 12, we have that S is greater than the surface of the prism, which contradicts the result obtained earlier which said that the triangle LFN, or the surface of the prism, is greater than the polygon in B. The format of the proof of proposition 14 is very similar to that of proposition 13. Many of the techniques used and propositions from Euclid used in the proof of proposition 14 are the same as those used in proposition 13. Therefore, I won't go into as much detail for this proposition. Note that in the proof of proposition 14, the results of propositions 9 and 10 are used in the places where, in proposition 13, the comments following proposition 12 were used. The pyramids that are constructed in each part can be constructed simply by using postulate 2 from Euclid to join the relevant points. In part 1 of the proof, we have that the polygons about A and B are in the duplicate ratio of their side lengths, which is a consequence of Euclid 620. Roughly speaking, these polygons can be split into an equal number of similar right-angled triangles with perpendicular heights equal to C and E respectively. Therefore, the sides of the polygons are in the ratio C to E, and so the ratio of the squares on the sides of the polygons is equal to C squared to E squared. And of course D is a mean proportional between C and E. Also in part 1 of the proof, we have the equality C to D is equal to the polygon about A to the surface of the pyramid excluding the base. This can be explained roughly as follows. The polygon about A is simultaneously the base of the pyramid. The perpendicular height of the triangles which make up the polygon about A have perpendicular height equal to C, and the perpendicular height of the triangles which make up the pyramid without its base is equal to D. Therefore we have, by proposition 8 applied to the pyramid, the polygon about A to the surface of the pyramid is equal to C times the perimeter of the polygon about A to D times the perimeter of the polygon about A. And of course by Euclid 6.1, C times the perimeter of the polygon about A to D times the perimeter of the polygon about A is equal to C to D. Therefore by Euclid 5.11 we obtain the polygon about A to the surface of the pyramid is equal to C to D. The remainder of this part is straightforward. On page 20, part 2, the inequality C to D is greater than the polygon in A to the surface of the pyramid excluding the base is given a brief explanation, and also another explanation is provided in the footnote of this page. I will here try to give a more full account of the derivation of this inequality that does not use knowledge of trigonometric functions. The polygon in A, since it's regular by its construction, can be split into a series of congruent right-angled triangles, each with hypotenuse of length C, and the pyramid can be split into a series of congruent right-angled triangles with hypotenuse of length D, and we necessarily have C is less than D. Let triangle PQR be a right-angled triangle congruent to one of those of the polygon in A, with PR, the hypotenuse, equal to C, and triangle UVW a right-angled triangle congruent to one of those in the pyramid with UV, hypotenuse, equal in length to D. Note that the bases VW and QR are equal in length, and it can be seen by cutting a length VV primed from the line VU equal in length to QP, and joining W and V primed that by Euclid 121, or some slight variation on it, that the angle VUW is less than angle QPR. Construct a right-angled triangle U primed V primed W similar to UVW, but with hypotenuse of length PR by Euclid 6.18, then PR is equal to U primed W primed, but the heights V primed U primed will be greater than QP, and so by Euclid 5.8 we have V primed U primed to U primed W primed is greater than QP to PR. Moreover, since U primed V primed W primed is similar to UVW, then VU to UW is equal to V primed U primed to U primed W primed by Euclid 6.4. Therefore by Euclid 5.13 we have VU to UW is greater than QP to PR. So with a slight variation of Euclid 5.16 we have VU to QP is greater than UW to PR. And by another slight variation of Euclid 5.7, porism, we obtain QP to VU is less than PR to UW. The bases of triangles UVW and PQR are equal, and so by Euclid 6.1 we have that triangle PQR to triangle UVW is equal to QP to VU. And so by Euclid 5.13, C to D is greater than triangle PQR to triangle UVW, and the inequality on page 20 follows. I find propositions 13 and 14 particularly interesting. In modern notation, we find that the surface area of the curved surface of a cylinder is given by the formula 2πRh. The form of this formula almost forces you to see this as the circumference of the circular base of the cylinder multiplied by its height, and there's nothing wrong with seeing things in this way. I think it's a perfectly normal thing, and it's certainly how I see the area of the curved surface of a cylinder put together. However, this possibly means that the way that a formula is presented to us can influence how we think about something, and may make it very difficult to see things in other ways. Proposition 13, in On the Sphere and the Cylinder 1, formulates the area of the curved area of a cylinder effectively with the formula pi times the square root of 2rh all squared. And this formula much more clearly emphasises the relationship that the area of the curved surface of a cylinder has with the area of a certain circle. This formula clearly has the form pi r squared, which is the well-known formula for the area of a circle of radius r. Of course, the square root of 2rh is the mean proportional between the side h and the diameter of the base, 2r. I'd personally find it very difficult, though maybe not impossible, to interpret the formula 2πRh as the area of a certain circle. I'm not suggesting that either way is necessarily better than the other, but simply that we can become very conditioned to seeing things in a particular way that we often miss the other ways that something can be viewed. And similar comments can be made about proposition 14, where we effectively derive the formula pi times the square root of RL all squared, where r is the radius of the circle at the base of the cone and L is the length of a generator of the cone. Thus the square root of RL is the mean proportional between L and R, and we can make a comparison between this form of the formula for the area of the curved surface of a cone and the more modern form, which is pi RL. I'll give a justification for proposition 15, but I'll use more algebraic methods to do so. That circles are to one another as the squares on their radii is Euclid 12.2. And we know by proposition 14 that the surface of the cone is equal to a circle of radius r, that's uppercase r, where h2 uppercase r is equal to uppercase r to lowercase r, with r lowercase r the radius of the base of the cone and h the length of a side or generator of the cone. So by Euclid 6.1 we have h times uppercase r to uppercase r squared is equal to h to uppercase r, and uppercase r times lowercase r to lowercase r squared is equal to uppercase r to lowercase r. Therefore Euclid 5.11 gives h times uppercase r to uppercase r squared is equal to uppercase r times lowercase r to lowercase r squared. Euclid 5:16, alternately, we have h times uppercase r to uppercase r times lowercase r is equal to uppercase r squared to lowercase r squared. Then again, by Euclid 6.1, we obtain h to lowercase r is equal to uppercase r squared to lowercase r squared, and moreover, the surface of the cone is equal to the circle of radius uppercase r by proposition 14. So by Euclid 5.9, we have the surface of the cone to the base of radius lowercase r is equal to the circle of radius uppercase r to the base of radius lowercase r. Note that the base of radius lowercase r is of course a circle of radius lowercase r. And by Euclid's 12.2, the circle of radius uppercase r to the circle of radius lowercase r is equal to uppercase r squared to lowercase r squared. So the surface of the cone to the base of radius lowercase r is equal to uppercase r squared to lowercase r squared, which by the previously shown, we have the surface of the cone to the base of radius lowercase r is equal to h to lowercase r as required. And note that Euclid's 12.2 simply says that circles are to one another as the squares on their radii. This is saying that the ratio of the areas of the circles is equal to the ratio of the areas of the squares on their radii. It's not suggesting that we seek a square whose area is equal to the area of a given circle, since this would be related to the ancient problem of squaring the circle. The first part of the proof of proposition 16 presents no real difficulties. Since, as we can see from the diagram, OA equals OD plus DA, then OA times AC is equal to OD plus DA times AC. And we can see OA times AC as the area of the region bounded by a rectangle with sides of length equal to OA and AC, and OD plus DA times AC as a rectangle with sides of length OD plus DA and AC respectively, and of course rectangles on the same base, AC, with the same height are equal. Using Euclid 2.1, then we obtain OA times AC is equal to DA times AC plus OD times AC. And using common notion 3, we get OA times AC minus OD times DF is equal to DA times AC plus OD times AC minus OD times DF. Now consider the two similar triangles OCA and OFD, as in the diagram on page 21. Then by similarity we have OA to AC is equal to OD to DF. Now suppose we have two rectangles both with base of length equal to OD, but with heights equal to OA and AC respectively. Then by Euclid 6.1 we have OD times OA to OD times AC is equal to OA to AC. And so we have by Euclid 5.11 that OD times OA to OD times AC is equal to OD to DF. Now suppose we have two rectangles both with base of length equal to OA, but with heights equal to OD and DF respectively. Then similarly we have OD times OA to OA times DF is equal to OD to DF, giving OD times OA to OD times AC is equal to OD times OA to OA times DF. And finally by Euclid 5.9 we conclude OD times AC is equal to OA times DF. Therefore OD times AC minus OD times DF is equal to OA times DF minus OD times DF, using Euclid common notion 3. And moreover, a simple geometric argument would easily show that for the right-hand side of this equality, we have OA times DF minus OD times DF is equal to DA times DF. Therefore it's easy to see that since OD times AC minus OD times DF is equal to OA times DF minus OD times DF, then OD times AC minus OD times DF is equal to DA times DF, giving OA times AC minus OD times DF is equal to DA times AC plus DA times DF. And Euclid 2.1 gives DA times AC plus DA times DF is equal to DA times AC plus DF. Therefore, OA times AC minus OD times DF is equal to DA times AC plus DF. And finally, to explain the conclusion, we can take the following steps. Suppose that the surface of the frustum is equal to the surface of a cone xyz. then the surface of the cone AOB to the surface of the cone DOE is equal to OA times AC to OD times DF, using the result from proposition 14. The surfaces of the cones are equal to the areas of certain circles, and circles are to one another as the squares on their radii. By Euclid 5:17 then, the surface of cone AOB minus the surface of cone DOE to the surface of cone DOE is equal to OA times AC minus OD times DF to OD times DF. Therefore, the surface of the frustum to the surface of the cone DOE is equal to dA times AC plus DF to OD times DF. So the surface of the cone XYZ to the surface of the cone DOE is equal to dA times AC plus DF to OD times DF. Now, since the surface of the cone DOE is equal to a circle with radius such that the square on the radius is OD times DF, then we must have that the surface of the cone XYZ is equal to a circle of radius such that the square on the radius is dA times AC plus DF. And since the surface of the cone XYZ is equal to the surface of the frustum, then we have that the surface of the frustum is equal to the circle with radius such that the square on the radius is dA times AC plus DF. As we can see, the lemmas following proposition 16 are all stated and proved in book 12 of Euclid's Elements. The proof of proposition 17 requires little explanation. It's worth noting that by Euclid 6.8, then the triangles DGF, DHG, and GHF are all similar to one another. We also have that GH is equal in length to OC by assumption, and the ratios derived are fairly clear. In proposition 18, what's meant by a solid rhombus has been explained earlier in the video. The perpendicular drawn from the apex of the second cone to one side of the first cone may require that the first side of the cone be produced. As we see in the diagrams, the side OB of the first cone has been produced to E, and DE is the length of the aforementioned perpendicular. The construction of triangle LMN can be carried out by means of the relevant propositions from Euclid, the details of which I'll omit here. Since LP is equal to OD, then by Euclid 5.7 we obtain LP to CD is equal to OD to CD. We have by lemma 1 that OC to CD is equal to the cone OAB to the cone ADB. Note that cones OAB and ADB have equal bases, since we're told that rhombus OABD consists of two cones with apices OD and with common base. Then by Euclid 5.18 componendo, we have OC plus CD to CD is equal to the cone OAB plus the cone ADB to the cone DAB. But OC plus CD is OD, and cone OAB plus cone DAB is simply the solid rhombus OADB. Thus OD to CD is rhombus OADB to cone DAB. The equality involving the ratio LP to CD follows from lemma 1, also since cones LMN and DAB have equal bases. Therefore, using the relevant propositions from Euclid, the equality labelled 1 follows. AB equals MN by the construction of triangle LMN, and surface OAB is equal to base of FHK by assumption. The equality base of FHK to base of LMN equals the surface of OAB to the base of AOB follows from Euclid 5.7, and also that by the construction of triangle LMN we have the base of LMN is equal to the base of AOB. Note that the triangles OCB and OAD are similar triangles since they are equiangular. Of course, they're both right-angled triangles, but they both have the common angle BOC, and therefore the two angles OBC and ODE must also be equal. Archimedes uses lemma 4 of page 22 to deduce that the cones FHK and LMN are equal since LMN is equal to the rhombus OADB. Then by Euclid's common notion 1, we conclude that cone FHK is equal to the solid rhombus OADB. The demonstration of proposition 19 is fairly straightforward. However, the jump from base of LMN equals the base of FGH plus the base of PQR to the cone of LMN equals the cone FGH plus the cone PQR is obvious enough using modern methods, but I'll provide a justification for this using ratios and proportion. Suppose that cone FGH plus cone PQR is equal to cone XYZ, where cone XYZ has height equal to cone PQR. Then by lemma 1, we have cone FGH to cone PQR is equal to base of FGH to the base of PQR. So by Euclid 518, then the cone FGH plus the cone PQR to the cone PQR is equal to the base of FGH plus the base of PQR to the base of PQR. Therefore, the cone XYZ to cone PQR is equal to the base of FGH plus the base of PQR to the base of PQR. Then by lemma 1, the base of cone XYZ must be equal to the combined area of the base of FGH and the base of PQR. Therefore, the base of cone XYZ is equal to the base of LMN. And so the cone LMN is equal to the cone XYZ. And so cone LMN is equal to the cone FGH plus the cone PQR. The demonstration of proposition 20 is straightforward and is very similar in format to the demonstration of proposition 19, so I won't go into any further detail with this proposition. So that brings us to the end of this video. And I think at this point you'll be starting to get the idea about how Euclid's propositions may be used to justify some of the steps taken. Going forward, I'll often use more algebraic methods to make the justifications rather than going through the constructions that may be required. In the next video, I'll be going through the remaining propositions from On the Sphere and Cylinder Book 1, where we'll see some of the propositions proved in this first part being applied. Please get in touch if there's anything that you want to ask about this video, and I'd be very happy to receive any constructive feedback. Thanks for watching.